which page am I on? I'm on 10. Okay. 65 on 511. So before 1859, rabbits did not exist in Australia. So this represents time. Is it, they want t? Yes, okay. So t equals 0. At t equals 0, population equals 0. That year, okay. So that year, they released 24 rabbits into the wild. Okay, so at t equals 0, population 24. Without natural predators, the growth of the Australian rabbit population can be modeled by the uninhibited growth model. We are given dp over dt equals a constant times the population. Okay, where p of t is the population of rabbits. Okay, so p of t, I'm taking notes, population, and t years after 1959, so t equals 0 represents 1959. When the rabbit population was estimated to be 8,900, so part A, population 8,900, okay, its rate of growth was about, okay, dp over dt is 2,630 rabbits per year. Okay, use this information to find k, and then find a particular solution of the differential equation. Fine, okay. So they're given that 8,900 is this, when this, the rate of change of the population with respect to time, is 2,630 rabbits per year. So algebra, so 2630 equals k times 8,900. I have my calculator ready for you. I was just working on statistics with one of my students, and inv norm. Okay, so I have 2630 divided by 8900. Okay, so then k equals 0.2955. Okay. Now I have to warn you that, where's my share button? Okay. I have to warn you that some books, I don't know this one, we'll see in a moment, I prefer 4 decimal digits for any rate of growth, constant rate of growth. Sometimes they round it up and they write 0.296. I prefer 4 decimal digits. This is more exact than that. It's going to inflate the population, whatever they're asking. But on the test, on the final exam or test 3, I will mention please use 4 decimal digits so we know. Let's see if they say anything about it here. Oh, where am I? Yeah, no, they are not telling us how many decimal digits. Okay. Okay, so when the rabbit population was this, okay. So then they say, use this information to find k, and then find the particular solution of the differential equation. So we didn't finish. So now the equation is dp over dt equals k. So I don't know which one to use. Any preference? This will be closer to the truth than this one.
Let's use the more exact one.
Okay, so 2955 times p. Okay, so now, of course, I will multiply both sides by dt and divide by p. So now you know that these steps can be done at once, right? because we've done it like 5 times or 6 times already. I have to multiply both sides by dt, and then I have to divide by p. Why? P has to be on one side, t has to be on the other. So if I integrate, like we did already so many times, this is always in this case, 1 over p, right? Equals 0.2955 t plus a constant c. And of course, when I solve, I get again is e raised to all this, so it's e to 0.2955 t times e to c. Now, I do have a point. The point is 0.24. This point will enable us to determine the constant. So 0.24 is the point we have. Okay. So when t is 0, again, this is 1. So e to c must be 24. So e to c equals 24. So then the absolute value of p equals 24 e to 0.2955 t, which makes sense. I'm sure from algebra you remember the model, right? It's a0 times e to whatever. So again, p should be plus or minus 24 e to 0.2955 t. Of course, stop, cannot be negative. So this is 24 e to 0.2955 t. Let's see what they want in part B. Find the rabbit population in 1900, which is 41, and the rate at which it was increasing at that year. Okay, so this is P of t. So P, to be exact, this is P of t, 24 e to 0.2955 t, and we want to plug in 41. What is going on? Gee whiz, 4,384,359. Well, 58 if you want. I can have 0.28 of a rabbit. Okay, then they are saying that they want us, so this is rabbits. Again, I caution you, it depends on if they used 0.2955 or 0.296, which I disagree with, but okay, so now they want us to determine p prime of 41. I have to determine p prime of t first. So this will be 24 times 0.2955 times e to 0.2955 t. I'll multiply this, 24 times 0.2955, 7.092. And then I will plug in 41. So in y equals, I want to put in this function now, 7.092 and e to 0.2955x. And I simply want to plug in 41, and it will give us 1,295,588 rabbits per year. Gee whiz. 295,578 rabbits per year. Okay, so now final question.
It's a lot of rabbits.
I know. Without using a calculator, they multiply very fast. They multiply at almost 30% increase every year. P prime of 41 over P of 41. So part C, P prime of 41 over P of 41. It cannot be anything else but that growth rate. What was it? 0.2955. That's what I said, roughly 30%. Yes, it's huge. So that's the continuous growth rate, 30%. Okay. I don't have anything else to say about chapter 5, unless you say we need more. If you say we need more, we'll find more. If you say we got enough, we'll definitely review for the test, of course. Then I will move on to the last chapter of this semester, functions of several variables. I need your input. Is that a yes? Is that a no?
I'm good to move on to the next chapter.
Of course, you will have questions on Tuesday. We can go back. But please finish up everything between now and chapter 5. Chapter 5 should be finished by Tuesday so you can ask questions, please. Okay, last chapter. Chapter 6, functions of several variables. This chapter has 4 sections, 6.1 through 6.4. I'm going to start with the simplest of all, 6.4. Okay. Now, what is 6.4 all about is what it's called regression or regression analysis. And we're going to look at 2 different types, linear, logarithmic. It's really not big of a deal. We're not going to do any calculations by hand, but I need to explain why the regression analysis is in this chapter. So let's suppose we collect data, and data is based on 2 variables, x and y. Let's say I take everybody's blood pressure, and let's say height, or weight, or anything else. But I collect an ordered pair on each and every one of you. First individual blood pressure, height, second individual blood pressure, height, third individual, and I plot these points. So this is x, the blood pressure, and this is y, the height, or the other way around, whatever I want to study. But let's say I get some points, and these are the points. This is called a scatter plot. And I realized that it kind of looks linear, like a linear relationship. As x increases, y increases. It could also look like this, which means as x increases, y decreases. I just pictured here a scatter plot with an increasing, in other words, a positive slope type of, if x increases, y increases. And it turns out that, and I'll show you the linear regression model in the calculator, it turns out that there is something called the line of best fit. And that is a line that goes through this cloud, through this scatter plot, and has minimal error. That's why it's called the best fit. It has minimal error in the sense that the distances squared from each point to the line, the distances squared from each point to this line are the minimum. So it's the sum of xi minus, I'm going to call, I'm sorry, y. I want to put y, of course. So the sum of, because we're talking about the y values. So y minus y bar is the minimum. We also call it the residuals, the minimal residuals. Okay, so why is this in calculus? Because finding the minimum is a calculus situation. So finding the minimum of this error is basically based on what? Finding the derivatives that equal to 0 and finding minimum. And that's how all the calculations are determined, based on finding the minimum of residuals. Okay, so all I would like us to do is illustrate